All right, hello everyone, and welcome to the Meet the Wrigley Faculty webinar series, and thank you so much for logging in. I'm Katie Shabostel, Development Director for the Friends of the Wrigley Institute. The accumulation of plastics is a massive threat to our environment, and we're very fortunate to have Dr. Megan Fieser from the USC Chemistry Department joining us this afternoon to discuss what her lab is doing to help solve the problem. Today's presentation is being recorded, so if you have any technical issues or need to leave for any reason, it will be emailed to you. Throughout Dr. Fieser's talk, please enter your questions in the Q&A box you'll find at the bottom of your screen, and she will answer them at the end of the webinar. So without further ado, I'm going to pass it over to Wrigley Institute's Interim Director, Dr. John Heidelberg.
Well, good afternoon, everybody. And I would also like to echo Katie and say how excited I am to have Dr. Fieser here giving this talk. And I'm very excited to hear what she has to say. So I'd like to keep an introduction to be very brief because I don't want to cut into her time. I want to hear more about what she's doing. But I will introduce very briefly Dr. Fieser, that she got her Bachelor of Arts at Washington University in St. Louis back in 2010. And looking up some information, I'll embarrass her and say I hear she was quite the softball player back then, and maybe still today. She went from there to get her Ph.D. at UC Irvine and got that in 2015 for a dissertation on the spectroscopic and computational analysis of rare earth actinides, actinide complexes in unusual coordination environments and oxidation states. From there, she went and did a postdoc at the University of Minnesota in Professor Tolman's lab, and then came to USC as a Gabilan Assistant Professor in Chemistry in 2018, and has been here doing tremendous work ever since. And I do want to say a few things that I've learned about Dr. Fieser, as she's been working more with the Wrigley Institute, is she is incredibly committed to the undergraduate learning experience, I believe, and setting up a learning environment to help young scientists thrive. And I think that's to be commended. And she's also just incredibly interested in everything about the environment and being out in the environment personally. And lastly, I also, as a Cincinnati Reds fan, I'll say I hear she's also a bit of a St. Louis Cardinals fan, and we'll let that one slide. But without further ado, I'll turn this over to Dr. Fieser to give her talk. Thank you.
Well, thank you so much for that introduction, and thank you all for coming and attending. I'm sorry, there's a plane going over my apartment right now that you might hear. And I will apologize in advance. I have 3 large dogs that might bark at some point, and I apologize. But I'm really excited to get the chance to talk to you about plastic pollution. And in particular, I'd like to give you all some ideas on how you might be able to address this pollution problem at your home, as well as what scientists are doing to help combat the problem. I hope that you can just see my slide. Great. So plastics were essentially adopted and invented in the 1950s, and since then they've transformed our lives. They can handle a wide range of applications. They're stable, they're really cheap to make. Ultimately, that has led to them encompassing almost every aspect of our lives. It's really difficult to imagine an environment where we might not use a plastic item. In particular, medical applications as well as food preservation has really been useful for developing countries, as well as lowering the overall weight to cars and airplanes that has really impacted fuel economy as well. So the idea about plastics transforming our lives means that they're not really going away anytime soon. But I'd like to bring a particular topic to your attention, which is disposable packaging, which contributes the most problematic instances of plastic pollution. You can imagine how many times you buy a bottle of shampoo or laundry detergent, or buy things that are already packaged for your use. And even if you are being very conscious about the environmental impact of what you buy, such as if you used a reusable bag to buy your produce, such as apples, you're not necessarily avoiding those plastic stickers on the apples. So it's almost impossible to go completely plastic free. And there's a lot of items that you don't necessarily know actually contain plastics, such as aluminum cans that have a plastic liner on the inside, as well as even tea bags have a plastic adhesive that connects those filters at the edges. The COVID-19 pandemic has not helped the plastic pollution problem. And while things like masks and gloves and face shields that are being used in an alarming number these days are really useful in combating the COVID-19 pandemic, it is not helping the plastic pollution crisis. And it's being shown that this is actually causing a lot more problems for plastic pollution, as these masks are disposed as well as these gloves. And even if you use a cloth mask, these are often made from polyester fibers that ultimately will end up in the trash once we get past this pandemic. Additionally, with closing restaurants, the increased number of delivery foods from Grubhub and DoorDash has only increased the number of plastic packaging used for food delivery. And these aren't the only problems that the COVID-19 pandemic has had on plastic pollution. Just like many other businesses, recycling centers across the nation have closed due to the health constraints of the pandemic on the workers that work at those recycling centers. And so although your recyclables might be being picked up, that doesn't necessarily mean that they're actually being recycled. And many of them may end up in a landfill, even though you put them in the recycling bin. So I think this is a really good opportunity to just address what exactly is a plastic. Now, you might be familiar with these recycling numbers that are in those triangles, and each number represents a different type of plastic, where just 5 most common plastics are used for 6 different numbers. I should say that plastic 2 and plastic 4 are the same type of plastic, but have a different orientation of those plastics. Plastic number 7 is others, meaning basically everything else. And so when we look at these plastics, they have different properties that lead to different applications. For example, plastic number 1, polyethylene terephthalate, or PET, is commonly used for plastic water bottles, while plastic number 2, high density polyethylene, is well known to work well for milk jugs. Plastic number 4, low density polyethylene, is very commonly used for your plastic grocery bags. And so each one of these numbers represents a different plastic property. Now, that still begs the question of what exactly is a plastic? Well, a plastic is a long organic molecule. I've depicted it as these beads linked directly to each other. This is a long organic molecule, and we call these polymers. The reason that we call these polymers is because they're made up of many different building blocks that I'm depicting as a blue dot. These blue dots are monomers, mono meaning one and poly meaning many. So it's a compilation of many mers or building blocks to lead to this long chain. And how these long chains interact with each other leads to ultimately different properties that lead to different applications. Now, I'm a chemist, so the way that I view this is more in the aspect of their chemical structure. So for example, this is a molecule ethylene that's linked by 2 carbon atoms that are at the ends of this double bond. When this is reacted to form a plastic, you can make polyethylene. So here are those 2 carbon atoms in ethylene, and you form a carbon-carbon bonds to make your overall long organic molecule. And you know these as plastics 2 and 4. So while you see these different applications for the different plastics, as a chemist, this is what I see. And each different type of plastic is used for a different purpose for many reasons. And what you'll notice across all of these different types of plastics is that many of them are prominently featuring these carbon-carbon bonds. These are extremely stable and difficult to break, which is why these plastics are so stable to our uses and why we were so excited to use them when they were brought into production in the 1950s. However, I'll show you later throughout this talk that this stability that has allowed long-term use of plastics is part of the problem of that plastic pollution, because these bonds don't easily break in our environment. Because plastics have been so useful and so stable and are cheap to allow us to do many different functions, the overall demand for plastics has increased exponentially. Since 1964, there's been a 20-fold increase all the way up to 2014 of production, annual production of plastics, where in 2014, there were 311 million tons of plastics produced in 2014. Across 1950 to 2015, this leads to an accumulation of 8.3 billion metric tons of plastics that have been produced. And of those, 6.3 billion metric tons of plastic waste are generated. And so a large component of the plastics that are produced end up as waste. Now, our group really likes to make this weight number a little bit more tangible, something that we can really kind of get a gauge on. And we like to choose large animals in that matter. So 6.3 billion metric tons of plastic waste is equivalent to 630 million killer whales. Now, if we'd like to put that in an even bigger perspective, there's actually only 50,000 killer whales in our oceans globally. So this overall number is quite large. Now, once our plastics are used, the question is what happens to those plastics? So in 2014, there were 78 million tons of plastic just for packaging produced. 32% of these plastics after use were leaked into the environment. So these are our oceans, our parks, etc. 40% of these end up in a landfill. 14% are burned or incinerated for energy recovery. And only 14% is ever collected for recycling. And this is already a challenging number and something that we really need to address. Of the materials that are collected for recycling, not all of those end up being recycled. For example, 4%, and these numbers add up to 14, not to 100, 4% is lost during processing. You could imagine things falling off of conveyor belts or out of recycling trucks, as well as ending up in the wrong bin, like plastics ending up in the paper waste instead of the appropriate plastic waste. So this material is lost. 8% follows what's called cascade recycling or mechanical recycling. What this means is that the plastic item is ground up and then reprocessed into another item. Oftentimes these items are lower cost applications. A good example is a plastic bottle being converted into carpet fibers. Now you might put your carpet fibers, your carpets in your house and use them for a period of time. However, those carpets are going to end up in the landfill when you're done using them. So while cascade recycling does delay the overall challenge of plastic pollution, it doesn't solve the overall problem as the materials end up in a landfill anyways. Only 2% of the annually produced plastics for packaging are in what's called closed loop recycling. For example, meaning a plastic bottle is reprocessed into a new plastic bottle. And this is a number that scientists are really trying to address and improve. So what does this mean for our future? As I said, in 2014, we were producing 311 million tons of plastic. By 2050, it's projected that we'll be making over 1,000 million tons of plastic per year. And what that's going to mean for the environment is that we anticipate that there will be more plastic by weight than fish in the ocean by 2050. And that's quite alarming considering everything that we've already seen of the environmental implications of plastic pollution. Not only that, but this increase in need and demand for plastics is going to take a much larger component and percentage of our annual oil consumption, making it harder to do other things with oil. Now, just because we project more problems in 2050 doesn't mean that we're not already facing extreme challenges for pollution in our environment today. For example, the Great Pacific Garbage Patch off of the west coast of California is essentially a plastic island. It's almost entirely plastic, and it is considered more than twice the size of Texas. This is an enormous island, and this is what it looks like. Ultimately, it's a compilation of plastics. And as I said, those carbon-carbon bonds make these plastics really difficult to degrade, and it takes much longer than our use. So we're using these plastics and throwing them away much faster than they could ever possibly degrade. For example, not so long ago, this Doritos bag was washed onto a beach. And if you look in the bottom corner, this Doritos bag was produced in 1979. And if you ask me, this plastic bag is holding up quite well for being 40 years old. And so these are sitting in our oceans and they're staying put. And it's overall, the environmental impact has been pretty clear. This has reached global attention as of late. National Geographic had this really great issue where they really posed the question, is it time that we need to start making the decision of, are we going to focus on our planet, or are we going to choose plastics instead? And the overall impact on animal life has been pretty clear based on images such as this bird that's trapped in this bag. And you really can't unsee the video of a turtle with a plastic straw stuck up its nose and trying to remove that. Now, it's important to note that these are the plastics that you physically can see. You can see this straw sticking out from the turtle's nose. But just as important as these large pieces of plastic, small pieces of plastic cause just as much harm. Microplastics has been a term that is for plastic pollution, plastic pieces that are less than 5 millimeters. They can be commonly mistaken as sand because they're such small pieces, and they come from a lot of different things. One big component of where microplastics come from is from washing your polyester clothing, and that's something we don't really think about when we wash our clothes, is small fibers ending up in the ocean, and that those are plastics. Car tires are another component. And another thing to keep in mind is those exfoliating beads in your skincare regimen are also contributing to overall plastic pollution. That's one of the reasons why those things have been banned in many, many places. Now, overall, microplastics have extended across the globe. They've even been found in Arctic ice, which is so shocking and surprising, indicating that the pollution has reached our entire globe and is a problem that we can no longer ignore. I started at USC in 2018, so 2 years ago. My group is just 2 years old, and our overall missions are fourfold, 2 of which are in the laboratory and 2 are outside of the laboratory. One of our main missions is to inform the public. A lot of information about plastic pollution and ways to solve this problem that you can do today are really confusing and hard to identify what actually makes a good impact. And we are committed to being part of that education to make it easier for us to make a difference. In addition, I'll talk about this later, but we organize 3 beach cleanups a year where we've adopted Hermosa Beach, and we really want to be at the front lines and decreasing the amount of plastics that end up in the ocean. In the lab, we're committed to developing methods that can make new degradable plastics that can act as alternatives to non-degradable plastics that are already being produced. And we need to do this in an economic way, in a fast way that can still create profits. Additionally, we recognize that plastics are still accumulating in our oceans, and they're still there, and we need to address new methods to better tackle handling those materials. So let's get started with just talking about different solutions that both the public and scientists can take to improve this problem. First of all, you can avoid hard to recycle plastics. Now, what exactly is a hard to recycle plastics? In my mind, if in your location a recycling center does not collect a particular type of plastic, then that might be a plastic that is a good one to avoid as best as you can. And we'll talk a little bit about why different locations only recycle certain types of plastics. Additionally, small plastics such as yogurt cups can be really difficult to keep on a conveyor belt. They're very light. It's very difficult to keep them in the plastic stream. And so you can consider how it might be easily transferred in a recycling center. We all know that we have to buy plastics at some time. So when you do, it's a really good idea to reuse it as many times as possible. Extending the lifetime of any plastic item is just going to overall delay it getting into the landfill or into the environment, and it decreases the amount of plastic that you actually buy. And so reusing over and over again will impact this greatly. These 4 topics I'll expand on throughout my talk. In one area, we really need to find better recycling methods. This is for both the public to put the right things in the plastic recycling bin, as well as for scientists to develop better methods. We can think about substitutes, so finding the right items to substitute plastics to make positive impacts on the environment, to clean up our environment, to prevent things from ending up in the ocean, as well as making degradable plastic alternatives that we can use that are better for the environment. So let's start with recycling. There is no nationwide rule for what should be recycled or how it should be recycled. Ultimately, the limitations of recycling for any location is based on the recycling center itself. Based on the size that it is, how it's designed, different recycling centers can separate different types of materials. This includes cardboard, paper, aluminum, glass, and different plastics. And it should be noted that there are technological ways of separating certain things, but this is still a very manual process. There are many workers at recycling centers that are sifting through our waste daily that help create pure streams of recycled material. At the end of the day, after our plastics go through these conveyor belts all the way to the end, they're bundled in different bales that are for different items. So these are plastic bales that are specific types of plastic. Now, typically for every 100 bales, one of these bales is opened up and diagnosed for purity. And so anything that isn't that particular type of plastic that's in that bale decreases the purity of plastic in this bale. A good example is if you're looking at a bale of paper waste and there's plastics in those, ultimately you have less paper in that bale. And when you go to sell these bales to other companies for reprocessing, they are going to give you a lower price because there's a lower purity of those materials. So as the public, it is important that we follow the guidelines that recycling centers give to us to keep these bales as pure as possible. That gives them the highest price to resell the bale, and it keeps them in business. Recycling centers going out of business is only going to hurt the recycling problem. And so we need to do our part to help them thrive. Now that's not so easy to do, unfortunately. It turns out that depending on where you live, the rules are different. And so just in LA County, this is only 5 cities in LA County that we can think about, 5 areas. Los Angeles is famous for accepting all types of plastic. And this is great, but not all areas in LA County can do this. Burbank and Santa Monica have very strict restrictions on what types of plastic they accept at recycling centers, with Santa Monica only accepting plastics number 1 and 2. And West Hollywood and Arcadia actually don't distinguish what plastics that you put in the recycling bin based on the recycling numbers. Instead, they tell you to focus on the overall shape of the plastic item themselves. And this is quite confusing to know what you need to do and when you need to do it. They do have some restrictions of things not to put in, but the guidelines could be a little bit easier to find. However, it is definitely certain that putting the wrong thing in a recycling bin makes it harder for recycling companies to stay in business. So when in doubt, throw it out. You need to learn the rules of your recycling center for your location to remove as much doubt as possible so that you can recycle responsibly and help recycling companies stay in business. Now, what happens once they go through those conveyor belts and are sold to another processing company? Oftentimes, these materials are ground up and used for different applications. One example is mattress foams that are commonly ground up into small pieces and then used as the padding underneath your carpets. Plastic bottles are commonly ground up and turned into fibers for clothing. This is an example of a jean pocket. Now these items are, as we've talked about, they are used over time and ultimately end up in a landfill and are thrown away. And hopefully by the end of this talk, you'll see that scientists are really working on ways to avoid these plastic items ending up in the landfill and instead using them as feedstocks for new plastics. In terms of substitution, it's really important to think about substituting useful products in for plastics. And if you can find the right things, that's really great. But it's also really important to not let marketing deceive you. Sustainability, green, eco-friendly, environmentally friendly, these are all buzzwords that are used in marketing to tell you that you're doing something good for the environment, when that's not always the case. One really strong example is the term biodegradable versus compostable. Biodegradable suggests that a material will degrade down into small pieces, while compostable ensures that when a material does degrade down into small pieces, it's safe for the environment. So while both types of materials break down into small pieces, biodegradable does not distinguish that those small pieces are safe for the environment. They might be, but we don't know necessarily. Even if a material is compostable, that does not mean that you can put it in your backyard or into a landfill and that it will degrade. Especially compostable plastics, a lot of compostable plastics are only compostable in industrial facilities. One really good example is polylactic acid, or PLA. Eco Products is a really great company that has produced many different products with PLA, such as compostable utensils and compostable cups that you can use in replacement of other types of plastics. However, this plastic must go to an industrial facility in order to degrade. So you need to establish compostable pickup wherever you establish these compostable replacements in order to solve the problem. If you start using these compostable plastics but continue to throw these into the trash can, you're not actually solving the plastic pollution problem, because these materials will accumulate in the landfills in our oceans just like other plastics. Additionally, it's really important to know the term life cycle assessment or life cycle analysis. Many companies will use important components of use and end of life of a product to tell you that their item is environmentally friendly. But it's really important that you have to consider the entire life of a product. This goes all the way back to the resources that are used to make that product, the energy and overall chemical costs of processing those materials into products, the environmental cost of distributing those materials, the use, and the end of life. A really good example is that the early assessment is showing that paper straws and metal straws are not necessarily better for the environment than the plastic alternatives. Additionally, BPA has also been a buzzword for negative health benefits of using BPA types of plastics. But just because a plastic is BPA free doesn't mean that the plastic doesn't contain a molecule that might have similar health impacts to BPA. Ultimately, at the end of the day, what I'm saying is that when you consider substituting, you want to find the right substitutes that actually cause a positive impact on the environment to support those companies. There are many really useful substitutes that are being promoted in the market. One example is that aluminum cans are the best example of successful recycling. Almost every can that you use today is made of 75% recycled material. Overall, recycling of aluminum cans is excellent. So it is going to be a better choice when you can use an aluminum can over a plastic bottle. Additionally, there are companies like Blue Land that will create these materials that you can buy a single bottle, and you can buy little capsules that you dissolve in water to create your cleaning products, and you only use the same bottle over and over, and you decrease the amount of plastic bottles that you buy when you buy your cleaning products. Other companies have created edible dishware, such as this edible cup, or this seaweed-based pod that is edible and has been used in a marathon, indicating that you could decrease the amount of plastic produced or plastic used in a marathon by these edible seaweed pods. Additionally, Lollyware has created seaweed-based straws that actually degrade within 18 hours, indicating that they aren't going to stick around in the environment and can potentially be useful for the environment. Now, I know I've told you so many different ideas or so much information about how to help solve this problem, and so much of it is confusing. Our group is working to develop an outreach website that educates the public on all of these topics, including a recycling page where we aim to be able to let you click on this page, look up your individual zip code. We'll show you which website to go to learn, and we'll also tell you what type of recycling guidelines there are for you, as well as give you key information on how to avoid negative replacements and to really make an impact on this problem. Now, this website is not ready yet. This is the overall link that it will be when it is ready, hopefully in spring 2021. You're welcome to follow my Twitter account. I will most definitely announce this website when it is ready. Now, in addition to talking about ways to improve, we also organize beach cleanups. And we've done 3 beach cleanups of Hermosa Beach in Southern California. And just 3 2-hour beach cleanups, we have collected over 12,440 individual pieces of plastic. So although this beach looks really clean, these are all pictures before we started. This beach looks clean, but that doesn't necessarily mean that there's not a lot of waste in the sand along the beach. And most notably, over 75% of those plastics over 70% of those pieces of trash are plastics. And we're really grateful to all of the volunteers that have helped us in our mission. We've accumulated lots of different plastics, and we do this in partnership with Heal the Bay. We adopt Hermosa Beach through the Heal the Bay program. We use this really great app called the Marine Debris Tracker, where we can actually click in what items that we collected, and it actually follows it on a map. This information can be sent to programs like Heal the Bay and other organizations who then use this information for policy development and communicate with the government on finding better ways to create new guidelines for recycling and others. It's important that while you are all welcome to organize your own groups, and we'd love for you to volunteer with us, safety first is really important. You need to have the right PPE to be picking up other people's waste. And if something could cause harm to your own health, you shouldn't be picking it up. But we can make a positive impact by keeping things from entering the ocean. Now in the lab, my group is an inorganic research group, and our focus is on what's called catalyst design. Now a catalyst is a molecule or a material that can bind to organic substrates. I've depicted them as a square and a triangle here. They can bind to these substrates and create and help facilitate the creation of a product. Most often, the use of a catalyst lowers the energy of a particular process. This makes it economically more feasible to make a product. And that's where we would like to focus all of our research to lower the economic cost and the energy cost to making degradable plastics, as well as degrading current plastics. Now you can change your catalyst and tune it to react with different types of materials. So you can change the shape of what binds into the catalyst and therefore what products you make. As a chemist, the way I view this is by changing the chemical structure of our catalyst. Each color in these particular structures represents a variable that we can change that will tune not only what these molecules, what these catalysts can react with, but how fast they are at doing it. And as I said, our overall interests are making degradable plastic alternatives and degrading current plastics in our oceans. When we're making degradable plastics, our particular interest is in making polyesters. In general, polyesters can often be very degradable as well as biocompatible, meaning that these are safe for use in medical applications and food applications and such things like that. Now, this particular plastic uses two different monomers or building blocks. And if you bind them together in a perfectly alternating way, you make what's called an alternating copolymer. And that's shown by these chemical structures. This is an epoxide, and this is a cyclic anhydride that can be bound together to make a polyester. Now, by changing what I've termed as these R groups, we can change the chemical structure of these building blocks, and we can hopefully impact the overall properties that these plastics can have. So we can tune this to have properties that might be useful for silly putty or balloons or styrofoam cups, straws, or even the pillows that protect your shipments from Amazon. Now, while these plastics can be really useful, it's really important to address that catalysts are absolutely critical to make this cheap enough to be done industrially so that you can actually buy the products themselves. And so our focus is on designing catalysts that are cheap, fast, and easy to use for the synthesis of a wide range of polymers or plastics. While we're doing that, we also want to address the accumulation of plastics already in our oceans. Now, we've talked about how a monomer can be used to create a polymer. That polymer can be used to create a product, and after use, that product can be ground up into small pieces. For mechanical recycling, which is mostly what is done today, these pieces will be converted into a downgraded product such as clothing fibers or carpets. What we want to do is develop better methods to close the loop and take these pieces all the way back to their original monomers, meaning that these plastics are new feedstocks for new plastics to be formed. It creates this cyclic loop. Not only does it decrease the amount of accumulation of plastics in our environment, but it also decreases our overall need for oil to make these monomers to then go on to the plastic. So it has many different overall positive impacts. Again, in order to make this efficient and cheap enough to do, we need catalysts that are better at doing this for a wide range of plastics, and that's what my group is focused on. And what's really important here is that we need to consider how our methods hold up to real used plastic. So we partner with recycling companies that are kind enough to donate used plastics. For example, this is from Verdeco Recycling, which is only about 12 miles from USC, and they've been kind enough to donate ground up PET bottles, the pellets that they process them into, and even used carpets. And you can see the difference in color between these materials. These have additives and dyes, and these are the pellets that they process them into. And we want to make sure that our methods hold up to these materials. Plastic pollution is a global problem, and it's going to require a collaborative effort. We need chemists, engineers, biologists, government, businesses. We need everyone to work together to solve this problem. The US government has already funded several centers that work on different aspects of this problem. NSF Center for Sustainable Polymers in Minnesota, as well as the iCoop Center that has just been formed in Iowa, have been doing some really great work to address this problem. And for me at USC, it's really special to be part of the USC Wrigley Institute because it gives me the opportunities to have conversations with different types of scientists from different departments so that we can work from an outside-in approach throughout the entire university to address environmental challenges of plastic pollution. I'm really grateful to the team that I have built over the last 2 years of graduate students and undergraduate students that are just as excited about tackling sustainability of plastic pollution as I am. I'm really thankful to the University of Southern California, as well as the Women in Science and Engineering group at USC, the Wrigley Institute, and the American Chemical Society Petroleum Research Fund for funding. And I really thank you for your attention. I'd be happy to answer any questions.
All right, Megan, thanks so much for that. That was excellent. We do have a couple of questions for you. So first, if you can talk a little bit about why all the plastic in the ocean gets conglomerated in places like the Great Pacific Garbage Patch, and why it's not just kind of floating willy-nilly.
Yeah, from what I've read, this has to do with the currents involved in the ocean. There's not just one plastic garbage patch. There's actually several, and it depends on how the waters move throughout the ocean. I would expect that oceanographers would know a little bit more about those movements.
All righty. Okay. And now we've got sort of a three-part question about marine plastics pollution. And so we're often told that that's really a problem, that's really Southeast Asia's problem. And we're told that it's a problem, it's present here, but not elsewhere. So can you talk a little bit about that and like whose problem is that? And kind of related to that is how big is LA? How big of a do we contribute to that? You know, how big a role does LA contribute to that problem?
That's a really good question. So I'll start with the first one, which is that the misconception that the problem is with Southeast Asia, or with Asia. Ultimately, historically, the United States has been sending plastic waste to Asia for a very long time. One of the ideas behind this was that it was beneficial because China would send us products that we bought, but then they would be sending an empty ship back to China. And if they could actually take something useful that they could use, then that would be beneficial for them. So they would take our plastic waste back, they'd do that mechanical recycling and make downgraded products, and then they would send those back to the United States. And that worked for a really long time. But they can only really process and recycle a certain number of plastics. And they hit a point where the accumulation of those things that they couldn't easily recycle built up, and they've no longer been accepting our plastic waste. So the idea that the waste may be accumulating over there may be true, but we're also sending it to them as well. So I think that that's a really important fact. Now the United States has to really address the fact that we can no longer ship our plastic waste elsewhere. So we're going to see the implications even more than we already are because they'll continue to accumulate in our country. The second question was about LA's contribution itself. As far as I'm aware, there's been no direct number that it is how LA has impacted it. The National Academy of Science, Engineering, and Medicine has actually created a coalition that is aiming to provide some information on the US contribution to the problem that will hopefully be coming in the next year. So we're still trying to put together numbers of how that is. Big cities are most definitely impacting plastic pollution across the country.
Got it. Okay. So in terms of scale, since we don't really know in terms of the micro to macro, we're just really still figuring all that out, right?
Right.
Okay, got it. Is there any way to address microplastics that are already present in the ocean? How do we deal with those?
That's the big question. I think that we're still trying to figure it out. We're still trying to figure out how different aquatic life or bacteria, microorganisms might actually deal with plastics in the ocean, where collection is another issue. I think that many scientists from different types of fields are going to have to be addressing this more and more. Not only dealing with what's already in the ocean, but preventing more from entering to going in from our water streams back into the ocean.
Okay. Why do you think recycling centers are closing in California?
Well, part of it is that there are a lot of manual labor in recycling centers. So just like a lot of other businesses, there are people that are in close proximity to each other that are creating harm for the COVID-19 pandemic. So the pandemic is separate. That is one aspect of, they're closed temporarily right now. So hopefully they reopen and all survive the economic problems of this pandemic. But normally it's really due to having to separate more things than they need to. If they can't get those high purity bales of materials, it's harder for them to sell at a high price, giving a reasonable profit to continue their function. And so I think making sure that we communicate with the public on what is the right thing to put in the bin to make their jobs easier is only going to make it easier for them to stay around.
Okay. What materials are being considered as a substitute for plastic, and which ones are both biodegradable and marine degradable?
There's been a lot of research recently on using seaweed as a base for new types of plastic materials. Using bio-based sources can be very useful, but not always. Using sugars has been used in general. That polylactic acid, or PLA, can come from soy and corn. That's one of those compostable plastics that needs to go to industrial facilities. So researchers are working on many different feedstocks to find, really try and identify what can replace certain plastics. But it's really difficult to do when you want something to degrade. It's really important that it stays intact when you're using it for the purpose that you want, and only degrades when you want it to, or over a certain period of time. So that takes a lot of clever design, and I think people have made some really profound discoveries in that area, but we still have a lot of ground to make. Kind
of a follow-up to that in terms of things being able to break down this great bond. Can you talk a little bit maybe about some microorganisms, some microbes that might be able to work on breaking down these bonds?
There's, this is a little bit outside of my field, but there are examples of microorganisms that can eat certain plastics, and they can use them sometimes as feedstocks to make new chemicals that we can then sell. And so this is where chemists can collaborate with biologists in a useful way, that maybe things can digest plastics to a chemical that then chemists can use to make a value-added product. And we're seeing a lot of those types of proposals coming into fruition these days.
So what about if we were just to make plastic a lot more expensive? I mean, right now it's pretty cheap. Would that help cut down on waste? That's not supposed to be popular, but has that been discussed?
There's lots of discussions about, creating some sort of increased cost for buying petroleum sourced plastics or non-degradable plastics, and giving incentives for degradable plastics. That's really hard to do without You know, we don't even have a nationwide rule on recycling. So having government step in to help with those creations of guidelines would be really useful. To my knowledge, there's not a lot of these types of taxes or higher priced things. And oftentimes finding the right substitute costs more money, which makes it not as accessible to the overall general public.
Right.
We want that to change ultimately.
Right. And it's amazing, you know, what you and your group are doing, and, you know, creating this whole new group of, you know, the next generation of scientists that they're doing. So what are the manufacturers doing? Are they involved in, you know, in trying to find alternative materials and things that might degrade more quickly?
Absolutely. There are many companies who fund those centers. So I worked as part of the Center for Sustainable Polymers as my postdoc at Minnesota. There are many industrial partners who not only funded research from center members, but they really directly were involved in interacting with these multidisciplinary centers. And so we definitely recognize that, you know, working with industry only makes better options. And we also recognize that in order to stay in business, an industry has to consider profits, and they need to stay in business. So those conversations of what industry needs to get things to the market, those conversations have to happen with the university. And so that's where collaborations are really key.
So you deal with some tough subjects and some scary figures and like things that can be kind of depressing. How do you keep hopeful?
You know, I work with so many wonderful people who recognize these challenges. It's not just people that are in my lab, but people who see our mission and volunteer for our beach cleanups. People, especially our young generations, they want to be part of the solution. And to me, I feel like it's partially my responsibility to help them thrive. And so as a professor, I'm hopeful because I get to work with some amazing students that I hope will drive the field even further than I can myself.
Great, thanks for that. We've got somebody who knows, why can't we just return to glass?
Glass is a really interesting question. So glass is essentially made from sand, and we actually have problems of accessibility of sand. Recycling of glass is also very tricky. You can imagine when you break glass, it becomes quite sharp. So you saw pictures of those conveyor belts on recycling at recycling centers, and broken glass oftentimes can really cause problem for the equipment. So there are many challenges with going to just glass itself that are sometimes worse than plastics. Many states actually don't recycle glass because of those challenges. So while glass can be useful in certain applications, it's not necessarily the right approach for disposable applications for sure.
Okay. And how, so can clean energy be produced from the incineration of non-recyclable plastics?
Incineration of plastics has been done, and it's done on a small scale, but it's important to know that you don't put a piece of plastic as kindling on your campfire. And you don't do that for a reason. There are many other better types of fuels for burning. Plastics are not great fuels, and it turns out that you actually recover more energy by doing mechanical recycling than incineration. That's also not thinking about the overall greenhouse gas effect of burning these plastics, which is definitely true. There are going to be emissions. And so incineration is not really the answer. It is done as one option, but we would like to actually get away from it.
Okay. How much of an impact does it make by, refusing to buy plastic water bottles? Like what are some of the most impactful things as consumers that we can do?
That's a really good question. I think that we have to consider, and it's really not a bad exercise to think about how much plastic that you accumulate in a given week. The more we accumulate, the more we buy, the more we drive the market, we encourage companies to continue producing them on a larger and larger scale. That's what creates the overall plastic demand. The more we buy, the more demand there is. So decreasing our overall use is important. And it's a compiled effect. It's the same kind of argument for voting. You know, you as one person vote, and sometimes you may feel like that one single vote can't possibly make a difference. But when that vote turns into millions or billions, all of a sudden you make a real impact. So you decreasing the amount of plastics and maybe having conversations with your friends and family on why you're doing it and what you've learned, and talks like this can overall lead to, you know, a plague of helping plastic pollution. And that's kind of what we want.
Great. So, and for the plastics that are really hard to recycle, why haven't we banned those? Like, I mean, I have to admit, I was a little shocked to hear about yogurt cups.
So ultimately, we desire these things. We keep buying them. And if we keep buying them and we don't have a useful replacement, and that's why part of our research is so invested in identifying ways to create replacements that are useful, that can just fill in the gap. You know, some of these plastics that are not easy to degrade are very useful for non-disposable options, like the interior of your car or the interior of your planes. Those will get used for long periods of time, but the overall contribution to waste is still there. We know that there are airplane graveyards in the desert that with plastics that are not degrading. So ultimately, it's a need for the product, and we need to either replace them with better alternatives, or we need to stop the need for that particular product.
Okay. Is there a way to harvest or collect microplastics from the ocean and prevent them, you know, from polluting things? Is there, we hear a lot about those in the news, but is there other ways that are working?
You know, I'm not myself familiar. There might be, but I'm not familiar with published methods. I think that there's a lot of different sources to microplastics, not only our sewage system from, you know, washing our clothes, but also one of those big components was just things off of the road that wash down into the ocean due to many different reasons, including rainfall. And so you're getting microplastics into the oceans via so many different sources. I don't know necessarily how you prevent it entirely. I'm certain that there are scientists who are working on different methods to do this.
Okay. All right. And this is I just got the time for one last question. So as long as plastics are able to be held captive in a landfill, is there harm to just keeping them there if we can figure out a way to not get them into the water?
If we can just put them in the landfill, and just leave them there. You know, because these take so long to degrade, you're going to eventually find an accumulation problem. Things will fill up, right? Landfills are not infinite spaces. And we already see that in our communities that we're running out of space, and especially in big cities for residential areas and other types of spaces. So I think ultimately that's not the solution. It is a temporary solution, but we really have to address breaking these plastics down.
Great. Thanks, Megan.
Thank you so much.
Bet I'll pass the baton back to Katie.
Yes, thank you so much, Megan, for such an informative presentation. And thanks to all of you out there for your thoughtful questions and participation. There's so much we can do together to tackle this problem. As I mentioned earlier, a link to this presentation will be emailed to everyone who RSVP'd. In fact, the webinar series is hosted on our Meet the Wrigley Faculty YouTube playlist, so go check it out. You can find the URL in the chat box. And a link will also be available through the Wrigley Institute's main webpage. Our next webinar will be on August 19th, and we'll focus on 2 of our marine research projects at the Wrigley Marine Science Center in Catalina. Dr. Dave Ginsberg will discuss his surveys of the island's incredible marine biodiversity, and Dr. Diane Kim will give an update on our kelp biofuel project. More details are to come, so keep an eye on your inbox and social media. Please feel free to reach out to me with any questions. My email was in the confirmation email you received. And thank you again for joining us this afternoon, and take care and be well. And we look forward to seeing everyone next time.